LBC-G from the Chongqing's paper.
Oh, yes.
Yeah. So when I set everything equal to 0, I got within 100 milliamp hours per kilogram, or sorry, I think it's watt hours per kilogram. Yes. But then if I put a separator with a normal thickness, I can get it exactly on the number. So I was wondering if that means I have an issue.
I don't know. I haven't worked out the numbers myself.
Okay.
You might want to consult with your peers and see where everyone is. Somebody just typed something in the chat box, did they? Or what?
I don't see anything in the chat box.
I don't either. Okay, looks like we're ready to start here. So we will. I don't know if we have all the class anymore. People are probably getting less interested in fuel cells than they were in other topics. So I will have an announcement to make, which is we have Mark Overback coming to talk to us about silicon alloy negative electrodes on Wednesday and Friday. I'll be sending you his PowerPoints tomorrow. So he found time to do this, which is a great thing. And I look forward to that. So I'll finish fuel cells today, then Mark will come, and then on Monday next week probably would be the last lecture, which will be on supercapacitors. I'm just going to do one day on supercapacitors, most likely. It might spill over a little bit longer, but it might not. Oh yeah, and Monday is Easter Monday, but Dalhousie operates on Easter Monday because we get Monroe Day off. So Monday is not a holiday for us here. Okay,
how's the homework situation look?
We have a homework due on Wednesday, right?
Yep.
And you'll have one more after that.
Cool.
Okay, can people see my screen?
We can see a slideshow.
That's what you should see. Perfect.
Perfect.
Okay, so I just want to go over the main features of a fuel cell and how it's operated before we talk about the fuel cell program a bit more. So I'll just remind you, you have hydrogen that comes in. It goes through a humidifier, which is just a water tank whose temperature you set. The hydrogen will come out saturated with water at that temperature. So that's how you control the humidity of the inlet hydrogen stream. This flows in and it goes into the gas diffusion layer. And the catalyst layer is here where my laser's moving along. So there's a difference in the hydrogen concentration. Well, actually no, because it's pure hydrogen. There's a difference in the moisture content from the front to the back. It will generally be more moist at the back and less moist at the front because there's osmotic drag dragging the water molecules along with the protons from the left side to the right side. If you have extra hydrogen, it will be exhausted out the bottom. On the other side, it's the same. You have air or oxygen coming in, which is bubbled through a bubbler again to humidify the gas stream. This passes through. And if it's air, the oxygen content will be large at the back and small near the catalyst layer because the oxygen is being used to make water. that water that's being produced and also being transported by osmotic drag has to be transported away in the gas stream to prevent flooding at the membrane, at the catalyst layer. So in principle, the kind of things you can control are the temperature of the cell, the thicknesses of the gas diffusion layers, the thickness of the membranes, the temperature of the humidifiers, the stoichiometric excess of air and hydrogen that are being supplied to operate the fuel cell at a particular current. And those are the kind of things that you can control. So any questions about this basic operation of a fuel cell?
Jeff, why do we need to humidify the oxygen side or the cathode side?
Yeah, the only reason that you would humidify the oxygen side is if you're worried about drying out the membrane over at this side. Just because you're running dry air over the membrane, you might dry it out at this side. In general, there's enough water being produced and enough osmotic drag to keep the membrane humidified.
I see. Thanks.
Okay, so what we're going to do now is we're going to have a sort of a class participation event where we operate the fuel cell program, and then I'll show you some problems, and you'll tell me what to change in the fuel cell operation to fix it. At least that's the plan. So I'm going to unshare my screen. And then reshare the fuel cell program. Okay, you should see the window for the fuel cell program. Is it true?
Yep.
Okay, so there are a few things that I didn't remember what they were last time. So I'm gonna go through those this time. So here we have a fuel cell that's set at 75 degrees C. You can see down at the bottom. I'm moving my mouse around there. At 75 C, there's a particular amount of water that you can hold in the gas stream before you get condensation, and that's what's shown by this horizontal dashed line. So if we lower the cell temperature, this dashed line will move down because the amount of water that you can hold in the gas stream without condensation becomes less. We'll do that in a while. And then there's these red lines and blue lines. This tells you the mole fraction of water in the gas stream at the membrane gas diffusion layer interface. So that's where the catalyst is. That's in red. And then also at the gas diffusion layer flow field interface, which is in blue. So anytime either the red line or the blue line crosses the dashed line, you'll get condensation and hence flooding. And that's where the water to sulfonate ratio lambda just kinks over at 14. So this current density of about 1.6 amps per centimeter squared is where flooding begins, as indicated here. And then we have the anode molar water fraction down below, and you can see that that is going down as the current density increases, and that's because of osmotic drag sucking water from the anode side to the positive side. Okay, so I want to set up the fuel cell in a way, and then we're going to try to, oh yeah, there's this other thing here which we should talk about. This curve, it's chi. Chi is the ratio of the water flux to the water being produced by the fuel cell reaction. The water flux means the water that's flowing from the anode to the cathode by osmotic drag and also just by diffusion. So here there's a lot of water flowing compared to the amount of water that's being produced at low current densities. So why is that the case, you ask? Well, in this particular setup of the fuel cell, we're running what's called variable stoichiometry. So it tells us we have twice the amount of hydrogen that we need and twice the amount of oxygen that we need to run this fuel cell. But those numbers are calculated based on the flow rates needed for 2 amps per centimeter squared. And at all the other current densities, the flow rates are not adjusted at all. So we're at low current densities, we're wasting a ton of hydrogen and we're wasting a ton of oxygen. Okay, so the first thing we're going to do is rerun this calculation with a fixed stoichiometry. So I click the fixed stoichiometry box, and what that means is at any current density, we have twice the hydrogen and twice the oxygen that we require to operate the fuel cell. Okay, so then you can see what happens to this chi. It will mean we're not blowing a ton of gas, a ton of humidified gas over the negative gas diffusion layer like we are in the variable stoich experiment. So we'll run. So now when you look at this water flux to water produced, it doesn't go up to 20 at low. If there was a change in scale, now it's around 1 the whole way. Okay, so who can tell me at what current density do you believe flooding is occurring now in this fuel cell?
Around 0.8 or something.
Yeah, so you're right, around 0.8. You can see lambda on the cathode side reaches 14 and then it's flat around 0.8 amps per centimeter squared. It's also where the red line crosses over the saturated water vapor pressure. So what that means is the polarization curve, voltage versus current density curve, will reach 0.8 and then just die. Will just drop off like a stone. All right. Okay, so I want to fix that. I don't want to flood anymore. I want to work under fixed stoichiometry with the fuel cell that I have. What should I do? You give me some ideas. What should I change to try to reduce the humidity at the positive side, but still, you know, keep a good fuel cell polarization curve?
Can we increase the cell temperature?
Let's see what that does. So we'll go, how far do you want to go?
I don't know, 90?
Wow, okay, we'll go to 90. Okay, so we're going to keep our eye on the polarization curve, the values of lambda, what happens to the flooding situation. So here we go.
I killed it.
You made the polarization curve worse. What happened? Why is the polarization curve worse now?
It looks like lambda for the cathode just flatlined.
And what about the anode too?
Oh yeah, it goes flat pretty early on.
Yeah, so lambda's really low, so it means the membrane resistivity has gotten large. So your ohmic overpotential is much steeper than it was before. So you don't flood, but by the time you get to 2 amps per centimeter squared, you're getting virtually 0 volts out of the fuel cell because of this huge ohmic overpotential. Okay, so how do we fix this? What should we do now?
You wanted to keep the thicknesses the same, right?
I don't want to move the thicknesses, no. I want to make this fuel cell as best as we can do. Okay, so if you think the cathode and the anode, the membrane is too dry, how do you make it wetter?
We could humidify it further. So
what should I do? What should I change?
if you decrease the humidifier temperature, no, actually increase it, because we want to increase the water vapor pressure inside.
Which one do you want me to increase, the anode or the cathode?
Anode would help more, I think, because the membrane is, the resistivity of the membrane is increasing.
Okay, so what do you want me to change the anode humidifier temperature to?
Yeah.
What number?
Let's say 90 or something.
Okay, I think that's a good choice. It's the same as the fuel cell temperature. So go to 90. Okay, so what I want to say is, you know, when we were doing our operation work on fuel cells, this is what would happen. We'd change something, and then we'd have to wait a half an hour for the fuel cell to stabilize and learn if it was better or not. It took so long to get the fuel cell operating, you know, just right. And then you would learn, well, it's not quite just right, and it would slowly flood over time. So developing this program made our lives so simple, because it's easy to just try stuff. So we're going to change to 90. So we're going to watch the fuel cell polarization curve. We're going to watch the lambdas, and we're going to watch what happens to the water content in the gas streams. Here we go. Okay, so look what happened to the ohmic overpotential. Dropped way down. It was up around 0.6 volts. Now humidifying the anode side made things way better. The lambdas went up to 10 at the negative, and you know, whatever this is, 7 or so. So that really improved the membrane conductivity, and now we've got 0.4 volts at 2 amps per centimeter squared. And we're not flooding, right? We're bringing in almost as much water as the anode side can hold. So we made a big improvement. Okay, so now I want to know what happens if I'm cheap and I don't want to send hydrogen out into the air wasted. What should I do?
Do you have to change the pressures?
No. How can I limit the amount of hydrogen I'm wasting?
The stoichiometric ratio?
Yeah, I have to change my stoichiometric ratio. So let's take the hydrogen down to, what do you think?
1.2 or something.
All right, we'll go to 1.2. Now realize when we do this, we also decrease the amount of water that's coming to the anode side, because the water is coming in the anode gas stream, and when we slow down the anode gas stream, we'll be bringing less water in. So we should see an impact of less water. The lambda should go down on both the anode and the cathode, because there should be less water around. And we'll see what happens to the fuel cell polarization curve here. So we'll run. So it wasn't that big of a hit, really, right? Didn't hurt us too badly. So that's a good thing. Can we go even lower? Why not go to 1.1? Still, it's decent, right? Okay, so we want to make it better. What can we do? We want to get this value of voltage at 2 amps per centimeter squared up. What should we do?
I think we could operate at a lower temperature as well in comparison to 90. Would
right.
that help?
What do you want me to change? The cell temperature, the humidifier temperature, both?
Both of them.
And what temperature would you like?
80 or something.
Okay, we'll go to 80 on both. Any other changes? No changes, so off we go. So watch what happens. Oh my God, it became much worse, right? Look at the ohmic overpotential. It's because our lambdas are too low. So what should we do now?
We'll have to either increase the hydrogen or increase the temperatures again.
Well, what happens if we just increase the anode humidifier temperature and bring more water in? Let's go to 85 and see what happens. And hopefully we won't cause flooding somewhere. Ooh, we did something. We have a glitch.
Wow.
I don't know what this glitch means. Let's try a different temperature and see if the glitch goes away. There we go. Don't know why. Anyway, that improved things back to about where we were. Right? So we want to get better than 0.3 at 2 amps per centimeter squared.
We haven't touched the cathode humidifier yet. Will that have a big effect?
We haven't touched the cathode humidifier temperature. Well, we could see what happens. See, we could raise the humidifier temperature a little bit because we're not quite flooded yet. That would help get more water in the membrane, and that might boost the performance a little bit, but we don't want to flood. We're pretty close to flooding. So maybe we don't want the anode humidifier so high, and then bring up the cathode humidifier a little bit. But anyway, we'll just move this up and see what happens. We'll go to 30. Seems okay, not much happened. Up to 40. See how long this would take experimentally with no clue of what you're doing. This is moving up. It's still moved up. Still not flooding, but super close. Go to 50. Now you're flooding. It's okay, so you flooded out. So you could reduce the anodes back to 80 and see what happens. Made it much, much worse, right? Not flooding, but we're not bringing enough water in. Okay. So it's really kind of interesting to play around and see what happens. So what I'll ask you to do in your homework is to find the optimum operating conditions of the fuel cell with certain parameters, like certain thicknesses of membranes and stuff, to give you the highest current density at 2 amps without flooding, 2 amps per centimeter squared without flooding. And it takes a while to sort of map that out. Okay, any questions about this? You know, we haven't played with the membrane thickness at all yet. We will in a few minutes. But for now, any questions about what any of these different graphs mean and what we're doing here? Really only Devia and Scott were speaking, so the rest of you, I don't know if you're in tune with what we're doing or not.
Jeff, I had a question about the stoichiometric ratios. So in practical operation, are they like kept equal for hydrogen and oxygen, or just depending on our requirements, we change them, or depending on which, like hydrogen would be more expensive, it would be stored. So how do we really manage them?
Yeah, typically in a real fuel cell, the oxygen is air, so it's free. So the only thing you have to worry about is the fact that you have to blow it through the fuel cell. So you have a blower that's blowing the air through the flow field. And if the flow field has a fairly small fluid channel, then you need a lot of power to run that blower. So you don't want the stoichiometric ratio of the air to be too enormously big. But on the other hand, if it's valuable for drying, keep combating flooding, then increasing this is a good thing to do. With respect to the hydrogen side, you just don't want to waste hydrogen. So running the stoichiometric ratio on the hydrogen as close to 1 as you can is the best thing to do. And when you're running fixed stoichiometry, it means every time you change the current density, you're changing the gas flow rate to match what's required. So it's tricky, right? It's a fairly tricky operation. Running the cell at a fixed current density is far preferred than going back and forth, up and down like crazy.
Yes, that makes sense. Thanks.
A question about the pressures, like the anode and cathode pressure. Right now it's at like atmospheric pressure. But if it was like in a vacuum, would it be better? Like you wouldn't have as much condensation?
You have to have enough pressure to run the gas through the fuel cell and then exhaust it on the outside. I think this is, I can't remember if this is gauge or absolute pressure here. But it has to be at least 1 atmosphere of absolute pressure. And normally it's more because you have to force the gas through the flow fields. I suspect this is 1 atmosphere gauge pressure, that what we see here, not 1 atmosphere absolute.
So it needs to be flowing.
Yeah, you have to blow it through. So I'll be sending you the paper that describes the program, and it tells you, the units of everything here and exactly what's going on. Okay, so let's move along. So go back to the PowerPoint now. So I'll stop sharing. And then I'll share the PowerPoint again, which I think is here. Yeah. Okay. Talked about this. Yeah, I was just showing on this slide how you detect flooding. Flooding, you see it here, you see it here. And what that means is the fuel cell polarization curve would just die at that point. It's not shown in the calculation. Yeah, this is showing what happens if you get dry out at the anode side. You get this big increase in the ohmic overpotential from the dry out. And you get this big rollover in the polarization curve because the anode is the membrane's drying out here. And you also have flooding going on. It's drying out at the anode side and flooding at the cathode side. Yeah, so there's an export button shown here. And the export button allows you to export files of all these things that we're seeing in those graphs, plotted as a function of current density. You get the voltage and all those different things in the different windows. That means you can make graphs like this. It's a really handy program. It's really quite nice. Okay, so this is from the 2010 Department of Energy Hydrogen Program Advanced Materials presentation. And they're talking about how to simplify a fuel cell system to get cost reduction. So this is what a fuel cell system going in a car in 2008 was proposed to be. So let's take a look at it. Got a compressed hydrogen tank, a valve, another valve, pressure transducer, diverter, blah, blah. And then you go eventually into the fuel cell stacks here. And you get exhaust from the anode side, which might still have hydrogen in it, which can come around, can be fed back in and sent back to the fuel cell. Then they've got a water reservoir, a water pump, a water spray air humidifier. They've got a compressor here to compress the air, which is coming in. Then it goes into a demister, and then the air goes into the fuel cell stack. So here, it looks like they're humidifying the air side, right? I don't see any humidification at all of the hydrogen side, which doesn't make much sense. And then they have a high temperature radiator system with coolant, because the fuel cell, remember, is only 55% efficient. It's going to self-heat a lot. So you have to cool it with a radiator cooling system. That's this black line here. Cooling loop. And then the air comes through, cathode exhaust. There's a condenser because it's full of water. So you want to condense that water out and so forth. So I would argue that this is a lot more complicated than the lithium-ion battery. Would anyone debate that? Okay, so simplification is the key to cost reduction. Let's see where we go. So in 2010, what happens? There's a lot less stuff here. We've still got cooling loop because we want to keep the fuel cell cool. We've got our compressor to blow the air through. We've got a humidifier, again for the air side. For some reason, we're not humidifying the hydrogen side at all. Don't know why that's the case.
Hey, Jeff?
But yeah.
Do you think they recirculate the hydrogen here that comes out of the fuel cell? I think it helps with hydrogen utilization. And if I'm not mistaken, I think this hydrogen is also carrying some relative humidity to basically humidify the anode side.
Well, that might be right. It might have picked up some humidity. But remember, because of osmotic drag, the water on the anode side tends to get dragged through to the cathode side.
Mm.
So anyway, it might be the case that it gets somewhat humidified by this loop that's happening here. Okay, anyway, it looks a lot less awful. So what were the changes? Membrane humidifier instead of water spray humidification. High temperature, smaller radiators. Oh yeah, they're operating at higher temperature, so the radiators are smaller. Lower pressures, blah, blah. So let's go on and see what happens next. 2015. Wait a minute. Holy doodle, what happened? No humidification. No humidification. Lower pressure, smaller compressor, no expander. Now it's getting to be pretty simple. Just have to blow the air through, keep it cool, and run your hydrogen loop. So how does the fuel cell work if there's no humidification happening? How come the membrane doesn't dry out? Well, anybody have an idea?
Maybe the water produced in the reaction is used effectively.
Say that again.
The water which we produce is used to humidify the membrane, maybe.
I guess that must be the case, but you know, we can, if we try to run fuel cell without any humidification, I can tell you lambda is going to go to 0 at the anode side with the fuel cell that we were using before. So we have to go to fuel cell and figure out what's going on here. This is why the program is valuable. So we'll do that. Yeah, so I said, holy mackerel, let's check it out with fuel cell. Fuel cell, sorry. So we'll go to fuel cell. Where is it? It's gone. Oh, there it is. Here it is. Do you see fuel cell again?
Yep.
Okay, so what we have to do is say no humidification. So to put the anode at 20, cathode at 20. Okay? You can leave the cell at 80 and run and see what happens. Well, that's the most ridiculous thing you've ever seen. I'm getting a call from FedEx. I have to take this, so just hang on a second. Jeff Don speaking. Good, what's up? Oh, yes. Yes, yes. It's a battery material. It stands for lithium manganese iron phosphate. Lithium manganese iron phosphate. Yeah. Okay, anything else? Okay, thank you. Bye. Sorry about that. I'm back. Okay, but anyway, it looks like this sort of crashed the program. Can you hear me, by the way?
Yep.
Yes.
Yeah, the lambdas are ridiculous here. So let's make these a little bit more reasonable, like 40, and see if it can operate at 40. Oh my God. I have to restart the program, just hang on. There we go. I probably have to reshare my screen. I don't know what you see right now.
Smiley face.
Smiley face, okay, great, I'm glad. Okay, so there's fuel cell again. So we'll run it under usual conditions, okay? So we want to make this thing operate without humidification. It turns out the way you do it is you make the membrane super thin. So it's 100 microns now. If you turn it to a 10 micron membrane, watch what happens to everything. Look at this. You're at 0.6 out of an amp at 2 ohms, 2 amps per centimeter squared. And you're flooding, sure. So we don't want to flood anymore. So we can increase the temperature to 90. And what's happened now? Oh yeah, we're in variable stoich. We need to go to fixed stoichiometry. Good. We still are having trouble with very low moisture content. I guess we have to increase we don't want to increase the anode side. If we go back to 80 and lower the anode side to 70. That's looking okay. See, the ohmic overpotential is really low because the membrane is so thin. And what if we turn it down to 60? We're still okay, even though the lambdas are low. We have such a thin membrane, we're okay. So when you make the membrane thin, you can get away with, if you like, murder. If I turn up the thickness back to 100 microns, you'll see that the fuel cell is a piece of junk. Yeah, so it just absolutely crashes by 1 amp per centimeter squared, and the ohmic overpotential is massive. So this is the key to running without humidification, is you need a thin membrane. So not unlike the lithium battery situation where, you know, from 1991 to nowadays, the separators got thinner and thinner and thinner, the current collectors got thinner and thinner and thinner. The same things happen in the fuel cell space. People learned how to make Nafion robust and really thin. And that allowed the fuel cell to operate with virtually no humidification, and in fact, no humidification at all in the 2015 and beyond case. So we'll go back to the PowerPoint for a second. How do I do that? Okay, I think you should see the PowerPoint again, do you?
Yep.
See the power? Yeah, okay.
Yep.
So the point is, how do you do this without humidification? So the point is, with fuel cell, without humidification, it's a disaster unless you make the membrane thin. So I wrote to Mark Debe at 3M and said, in the cost estimate PowerPoint you sent me, I noticed in 2015 there will be no humidification of either the cathode or anode inlet streams. I then played with our fuel cell software to see how this might work. I conclude that integral to this strategy is a very thin membrane, 30 microns or less, so the cathode water can diffuse effectively to the anode side, keeping lambda at the anode high enough. Oh yeah, what we should have done actually is decreased the cathode stoichiometry so we weren't sweeping the water away so fast. That would have helped a lot. And to overcome osmotic drag. Running both the air and hydrogen at close to stoichiometric, so there's insufficient gas flow to dry out either side of the membrane. Doing this seems to work well. Do you believe this is the strategy plan? Jeff, you're right that thinner membranes are critical for good water management, not only at high temperatures, but under cool and wet, especially for ultra-thin NSTF type electrode. Blah, blah. The typical thickness of supported or reinforced membranes should be reinforced in automotive fuel cells today in the range of 15 to 24. the cost scenario plan for no humidification, but whether they can get there or not is a big question. I'll take a look at the fuel cell program, thank you. Can't you change the name? It's rather disparaging, don't you think? Thanks, Mark. Okay, so you guys have to realize who Mark Deby was. I mean, he was the leader of the 3M fuel cell program. He was like one of the top 4 or 5 fuel cell guys in the entire world. So we were really fortunate to have a chance to work with him for 10 years. It was a fantastic learning experience for me, and it was awesome. So this is the point. You can do it with a thin membrane, and we were running in the fuel cell program just too much, far away from stoichiometric, so we were drying out the membrane, right? And that seems to be the end. That is the end of the fuel cell segment of this course. So people have come a long way with fuel cells. It's simplified the way they operate in a fuel cell stack for a vehicle to be quite tolerable. But the biggest issue for me with fuel cells is the efficiency side. No matter what you do, if you insist on hydrogen from renewables, if you insist on hydrogen in a compressed storage tank, and you insist on using a fuel cell, the overall efficiency is going to be around 35%. And that's a problem. So whether fuel cells take off in a big way or not really depends on how much the oil companies promote fuel cells and promote hydrogen from fossil fuels by steam reforming of methane and other methods of making hydrogen from fossil fuels. Because right now the hydrogen fueling stations in California are all being supported by Shell and installed by Shell. Okay, so any comments and questions about fuel cells? Fuel cell part of this course? Anyone ever driving a fuel cell vehicle? I have driven in a fuel cell vehicle with Adam Timmons at General Motors. He rented he didn't rent, he borrowed the fuel cell vehicle that GM had on site at their Michigan R&D campus, and it was absolutely fine. It was just like a normal car. Drove perfectly, totally quiet, really quite cool. So as long as you have, renewable hydrogen, it's fine.
Jeff?
Yeah.
I have a question about your driving experience in a fuel cell car. Did you have to wait a couple minutes when you started the car, or can you drive right away?
You could drive right away because it has a battery as well, right? There's a battery for regen braking and also to deal with the warm-up period. So you could just drive right away. It's kind of like a hybrid, a plug-in hybrid in a way. I don't know what the battery range was in total, probably a few kilometers or so. But it was able to drive right away from the start.
Okay, I think that makes sense with the battery. I once heard that in the Toyota Mirai first gen or so, you have to wait maybe 2 minutes or so for the fuel cell to kind of equilibrate or something, but I don't know. This car, I think, also would have a battery.
I believe that would be the case from my experience with fuel cells. It takes a while for them to stabilize. But with a thin membrane, things are way, way better than with a thick membrane. That's for absolute sure.
Right.
Can you comment or compare polymer electrolyte membranes to solid oxides in solid oxide fuel cells?
Well, solid oxide fuel cells operate at very high temperature. They operate up at 600 or 700 degrees C. And a solid oxide fuel cell uses a oxygen conducting membrane, not a hydrogen conducting membrane. So the oxygen is being conducted from the positive to the negative through the oxide ion conductor, oxygen ion conductor. But apart from that, they're relatively similar. You feed them hydrogen and oxygen, you get electricity. Again, you have to worry about overall efficiency of the whole thing.
I see. And are all commercial fuel cell cars made with a polymer electrolyte membrane for proton conduction?
Yes, as far as I know, that's the case.
Okay. Is there a cost advantage or an efficiency advantage there?
Oh, by far. I mean, it's just an operational thing. You don't. How would you do this 600 or 700 degrees C fuel cell in your car?
I see. Okay, I didn't realize the temperature was that high.
That would be sort of awful.
Yeah. Okay, thank you.
I would add to that the solid oxide fuel cells are even worse when it comes to like restarting them, because of the you have solid materials and the expansion coefficients have to match up and stuff. So if you cool and heat up again, it will crack the different layers and stuff. And so it's really good for stationary constant power kind of running.
I see. Thank you.
That's good, Ron. Thanks for that comment. Yeah, I was online somewhere, I don't remember where, just the other day, and there was a commentary about fuel cells, and a lot of people were giving them a big trouble, about efficiency and cost compared to battery. But I always contend that if you have windmills turning and nowhere to put the electricity, you may as well make hydrogen. And then you can use that hydrogen wisely afterwards, which might mean running it through a fuel cell to regenerate electricity. So I think there's a good role for fuel cells, but maybe they're not the very first choice for everything. But they're certainly good. It's easy to store hydrogen gas in a big bag somewhere. Okay, so we'll have Mark on Wednesday and Friday, and then we'll finish off with SuperCaps Monday and perhaps the Wednesday after. And like I say, there'll be one more homework. I know everyone loves the homework so much, so I'm surprised you only want one more. Okay, see everyone later.